How's everyone doing? To introduce myself, who am I? Basically, I'm a software engineer at Databricks. I'm on the stream team, so what we do is our team motto is we make your streams come true. We work on structured streaming as well as Databricks Delta, so we can actually call ourselves the dream team as well from this point on. I'm an Apache Spark committer, so any questions you have around Spark, I can help answer after this talk as well. I studied management science, did a master's, was going to do a PhD, but then decided to join Databricks instead. And I'm originally a mechanical engineer, so please don't ask me like JVM, GC questions, but I can help answer data pipeline questions. So as a mechanical engineer, what I did today was I built a time machine, right? So what I would like you to do is, today we're going to write a time machine. And I'm going to take you all the way back to 2014, a long time ago. So what we had at Databricks as a data pipeline back in 2014 was pretty ancient. It's so ancient that I had to use Roman numerals to specify the year. But basically what we did was we had our services running on the cloud. They would write out logs, and then we would run cron jobs to S3 copy, S3 sync these logs from on the machines to S3. And from there on, we would use Spark in Databricks, running batch jobs every hour to process all this data, turn JSON logs into nice Parquet tables, all the way back then. And then we would use Databricks, again, to analyze all our logs, figure out if there are issues, see how our customers are using the product, and so on and so forth. So, mind the asterisk. So, data pipeline V1. First data pipeline at Databricks. It took one engineer about 1 week to implement. But this one engineer is like the creator of Spark SQL, structured streaming, and Databricks Delta, so calibrate accordingly. It was pretty robust for the very early days of Databricks. The problem was, it was pretty robust until we got to like 30 plus customers. File listing on S3 quickly became such a bottleneck that our hourly batch jobs started taking 8 hours just to list all the files on S3. So, this was not going to scale for Databricks. So fast forward to 2016, I graduated, and as a new grad, Databricks said, hey, you're a new grad, just build our next generation data pipeline. It was like, great idea. So what I did was I went to a lot of data engineering conferences, saw like what people do, and across the whole, tech world, people were doing the exact same thing, they just called things differently. So, there was this Lambda architecture. People were like centralizing their data in something like Kinesis or Kafka, and then they would use Spark to, do like streaming analytics out of it, and as well, write batch jobs, push the data into Hive, and then, query Hive. So that's pretty much what we copied. We just didn't use Hive. We always used Spark. And then we would, we built our Lambda architecture. We streamed continuously, and then we compacted data once a day. Then used Databricks to analyze our data. It was perfect, or was it? So it scaled very well, and the ETLing the data itself became pretty fast. So we were good there, but it had a lot of problems. First of all, it took two engineers about 8 months to build. It wasn't just the analysis logic. It was more we built this service called LogDaemon, which we shouldn't have. It's we could have used FluentD or Logstash to upload files, but young, dumb, and broke, like the song. That's what we did. So it took us 8 months, and what we observed was the query performance and the experience just got a whole lot worse. And some of the reasons for that was, we would have lots of small files for the very last day of the data. And then we would, we knew that this was going to be a problem, so we had compaction jobs. But the compaction jobs impacted in-flight queries, which was also another problem. We would, run reports every night, but then, the compaction job would take 1 hour longer and all our reports would fail. So we had this dependency that we had to deal with, which we hopefully didn't want to. Then we also observed like the HiveMetaStore quickly becoming the bottleneck. It's like we have this like one table, let's say it has like 300,000 partitions. Just like querying the partition information from Hive took about like 40 seconds. And then once you get the partition information, you also have to list all those files on S3, which is like already super slow. It's like it became intractable. Also, with Hive and Spark, we had to use this like refresh table thing. Refresh table is basically, since Hive is like so slow for this like metadata information, we would cache the information in Spark. So whenever your table needed to be updated, you would run this thing called refresh table. Or when you were writing data to like a directory on HDFS or S3 and you didn't call alter table add partitions on Hive, you would have to run this like MSCK repair table, which had to list all the files and figure out what were new partitions, and that was also annoying. Another thing was like this logic became a lot more complicated. We had this like Lambda architecture, there was like streaming jobs, batch jobs, and the pipeline was less robust. It was like more open to like failure. And fixing mistakes in the data became harder. So I'd like to give you an example of a data mistake that we had, which we could not fix. So can you see what happened here? So we have like some value, it's like going down. It was like going down for the weekend and it's like going up again. And then on Sunday, like those last 2 days, it seems like we don't have any data. But we do, it's like a very small line there. What happened was somebody just changed the unit that something was logged from like megabytes to gigabytes, so we got like 1/1000th of the data. The CEO was like, what the hell's going on? He just walks down, asks questions. We're like, sorry, man, it's like we couldn't catch it. And like, so for 2 weeks of data, we had this like usage report going all the way up, all the way down, and then back up again. So other like mistakes that we made in like our data processing pipeline, it was like schema inference and like mismatches were a huge pain. It's we didn't follow like best practices in the sense of like, okay, it's a ETL pipeline, so we need to actually fix our schema or like keep our schema stored somewhere. We were always doing like auto inference on like JSON files. And after like Spark 1.6 to Spark 2.0 upgrade, what happened was JSON files would, JSON schema inference would, find integer columns, and to be safe, just like cast it to a long column. Then we had all these like files before Spark 1.6 that had integers, 2.0 longs, and then when we used Parquet to actually query the data, it always threw exceptions saying that, oh, I can't read an integer to a long, and that was annoying. Another case we had was like a different type of log got introduced into the system, and suddenly we got like a table who had like 8 columns, suddenly had 32, and like it was all nulls. That was also annoying. Then there's this problem with, partial failures or like partial results, where like our pipeline wasn't as robust, so we would start writing out data. And then, we would lose our machines, and then with spot price spikes or whatever, and then suddenly we had all this like data lying around, so we get duplicates. So these were all annoying issues that we wanted to fix later on. So I've compiled this list of problems in data pipelines. I'm not making all of this up. There was a talk, like 2 talks before me, who had like 80% of the same problems listed above. So I've categorized it into 2. So there's like, first of all, you have correctness problems. The high-level problem there is like the lack of atomicity leads to pockets of duplicate data. When you're writing something out, you want to make sure that it either appears all of a sudden, or if there's a failure, it just doesn't appear at all. It shouldn't affect your results. The bookkeeping of what to process is like tedious. It's like you would get data out of order, you would get data uploaded from 3 days ago. Just figuring out what to process, what files are new. Like you had to list all those files. It was, again, like super expensive. You need to keep track of it somewhere. That was a problem. Schema management, we said, okay, it's hard to keep track of schemas. We need to keep track of it somewhere. We need to know if a schema change is safe, or if it's a new column, if a new column gets deleted, we need to make sure that we're compatible with the old data. That was a high-level problem. And then maintaining data hygiene. was also a high-level problem that we come up with. Basically, what this means is that everyone makes mistakes. We had the megabytes to gigabytes conversion. You need to do these like sanity checks, and then once you do these like sanity checks, these generally happen after the fact that you've written the data. So you need to be able to go and correct it. Can we actually do these checks at write time instead of during after the fact? So we don't have to fix anything, we'll just know. So this was like a high-level problem that we wanted to solve. With regards to performance, I said, okay, listing files on blob storage systems is slow. Okay, we got that. Lots of small files hurt query performance. Okay, that makes sense. And then the HiveMetaStore experience is horrendous. It doesn't scale well for us, and like having to call these additional things, it's expensive. So we wanted to solve most of these problems. So in 2016, we introduced structured streaming. So structured streaming was Spark's new streaming API built on top of data frames and data sets. And what we wanted to say with structured streaming was that you only have to care about your business logic, and then structured streaming, the system will care about incrementally running your queries on your data. So you don't need to do this bookkeeping all yourself. So how did structured streaming affect all these problems? First of all, with structured streaming, we would write a manifest file to commit data to our file sync. So we didn't have this atomicity problem anymore. If it failed, it failed. Once we wrote out the files, we would make a commit saying that these files are new, please read these files. Then with structured streaming, we also handled the bookkeeping process. Keeping track of what data is processed, that's totally structured streaming's job. You don't have to do anything about it, you don't have to care. And then we added watermark support to structured streaming for aggregations. This would allow the correct processing of data when things came out of order or came late. Structured streaming didn't solve any problems regarding schema management, but it actually made the data hygiene problem a little bit worse, because this manifest file was only writable by a streaming application. So all these like backfills that you wanted to do, which were batch jobs, these wouldn't get picked up by Spark anymore. So this problem became a little bit worse. Regarding performance problems, the manifest file said which files we need to read to make sure that we have all the data from the table. So we didn't need to handle file listing anymore. It was all there. And but what got worse was basically with streaming, we had all of these small files, and then we couldn't do compaction anymore with streaming. So that kind of hurt query performance. And it didn't do much about the HiveMetaStore. So we're like, okay, we need something better. So what do? We introduced Databricks Delta. So with Databricks Delta, it's our cloud storage offering, and it separates compute from storage. What that means is you write your files to S3 or Azure Blob Storage. You get priced on that. And then you only buy, like all the EC2 machines or the Azure VMs that you need to do to actually process the data. You don't need to buy boxes and like over provision on like storage or compute. It's like you use what you need and you pay what you use. Pay for what you use. So with Delta, we also completely removed the dependency on the HiveMetaStore. We said, okay, we're going to manage our metadata internally. We just got to get rid of this HiveMetaStore. The HiveMetaStore will only be a pointer to a Delta table so that people can actually find where the data is located with table APIs. So with Delta, we can scale to billions and maybe even trillions of partitions and or files. And this is because the way how we manage the metadata internally. And if you have billions of files, just use a larger cluster and then we'll scale accordingly. Another thing was it supported batch or stream reads and writes. So you could batch write into it, batch read from it, stream write into it, stream read from it. It basically simplified pipelines a lot. When you could do all these like operations, backfilling, streaming, both in and out of Delta. And the way it supported all of this was through ACID transactions. So you solve the atomicity problem again. So you don't have garbage data anymore. You can have multiple writers writing into Delta at the exact same time, And then if they conflict, we're going to fail one of the writers. But if they don't conflict, like if you're only appending new data, all of those can go in. It can go in from like 5 different streams, 5 different batch jobs running at the exact same time. Also, we built inbuilt support for compaction and indexing in Delta. All you need to do is write a SQL command that says optimize. And optimize will optimize your data layout on the blob storage. And one of the cool things about Delta with its indexing, which we use z-ordered sorting to do this indexing on, is that it's not a property of the table. You can do your indexing on each partition individually. So as your use cases change, as your business needs change, you can adapt according to these differences with different kinds of indexing. If you need to query different columns now, you don't need to rewrite the whole table anymore. You get all of this out of the box. On top of that, Delta handles schema internally, and it basically makes sure that whatever you're doing, it's safe. It also supports invariance, and by invariance we mean like, hey, this column must not be a null. So when you're writing data and this column's a not null, but for some reason you have a null value, we'll just fail to write. Or you could define like enum types, arbitrary SQL expressions on your column to make sure that your data fits what you expect. Another thing is tables auto update and provide snapshot isolation. You don't need to run refresh table anymore. You don't need to run MSCK repair table anymore. Whenever something new comes in, you read from it, you get it. If you're reading, but then something new comes in, you read the old data, stale data. It also supports harder operations like delete, update, and merge. Merge is also known as upserts. So it's like either an insert or if the key exists, update these values. So this fits in very nicely with CDC when you're trying to migrate from Oracle or MySQL into the cloud. You can actually connect to use all these operations to replicate your data on the cloud using Databricks Delta. It also leverages data locality through DBIO caching. So HDFS users, you can say, after this second read, you'll have data locality, so you won't have to read from the network again. So this also gives, great performance boosts. And coming in Q4, since we're on a time machine, I can tell you the future. We're going to support querying old versions of the table and also rollbacks on your data. If you make a mistake, just roll back to yesterday. Or if you want to figure out how many customers you had yesterday, just query it using as of yesterday. This is all coming in Q4. So let's go back to our problems. So correctness problems. ACID transactions solve the lack of atomicity. Then structured streaming still handles the bookkeeping of late and out of order data. Delta manages the schema, so schema management is not a problem. And it allows safe or evolutions, and you can opt into these. And then maintaining data hygiene is made easier by commands like delete, update to delete or fix records. And invariants basically protect you from corrupting your data in the first place. Then with performance problems, Delta doesn't need to list files anymore. It keeps its file information in its state. So all of these operations, you're not going to do all these costly S3 list queries. In addition, Delta's optimized method compacts data without affecting in-flight queries, so you don't have lots of small file problem anymore. And then the HiveMetaStore would just cut it out, so the experience is not horrendous anymore. So the way we have Delta set up in Databricks is that now we had data coming in from Kinesis, streaming data, then we had batch jobs coming in from S3. We would put all of these in a raw table in Databricks Delta, which was this humongous size table. And then we would shoot off smaller streams out of it and maintain these materialized views or summary tables. And what we do is these raw tables, we just keep around for a couple weeks. The summary tables, they're aggregate data. They're small, so we can keep them for a much longer period. And they also provide the more of the value. And our analytics and reports can be built on top of these summary tables. But with 2017, we started having new requirements. So we launched Databricks on Azure, Azure Databricks. So we had to change our data pipelines again because we couldn't just leverage Kinesis. And we had to replicate our pipeline in many Azure regions. And then there was this guy. This guy. There's more. It's like, did it haunt you too? It haunted me. Yeah, GDPR. So with these new requirements, we kind of evolved our data pipeline to this more futuristic word art version of 2018. Basically, we had like our AWS pipeline still leveraged Kinesis, and then we would put it into Databricks Delta. And then we had these, so we started uploading files to Azure Blob Storage, and then we don't want to read or list these files again, so we built event-based connectors for both S3 and Azure Blob Storage, and I'm going to talk about these right now. And as you can see, we had this new multi-hop pipeline where you had these bronze tables, which were the raw tables that I was just talking about. Then we would go into these like silver table concepts, which are more refined, and then gold tables, which are like basically the most aggregated, most useful tables, and then create our reports off of these. And every blue line in this step is a structured streaming job along the way. So the event-based file sources, we built S3 SQS on AWS, and the ABS AQS is going to be released on Azure with GDPR 5.0. What happens is basically events, as blobs appear on these blob storage systems, events are published to SQS in AWS or AQS in Azure. Then Spark, or structured streaming, will read these events, and then these will be our file pointers to what is new. And using this, we can read the original files from the file system, blob storage system, and just process those files. We don't need to list files anymore to figure out what's new. All these event-based notifications are going to give what's new to us already. So we solved the file listing problem again. And the properties of the bronze, silver, gold tables were that bronze tables, there was no data processing. And basically, the goal here was we would do some like deduplication because our Kinesis pipeline was like at least once semantics. And then we would also do this JSON to Parquet conversion. And that's it. We didn't do any other processing on this. And we keep this data around for like a couple weeks to fix mistakes just in case. Now, silver tables, these are the directly queryable tables by our engineers, data scientists, and whomever. Basically, what we do is we do the PII masking and redaction that we need to do in these tables. And then from the silver tables, we can derive the gold tables. And these are the materialized views of the silver tables. And these are basically the curated tables by the data science team, which business analysts or PMs could query directly. And to deal with GDPR, basically Delta's inbuilt support for delete and update basically made these DSR requests tractable. So we could just delete or update the records, and then 7 days later we run vacuum and the data's gone. So solved. You could check out this blog post once these presentations are deployed online. Check out databricks.com blog for the GDPR blog post. So with our data pipeline v3, basically the event-based file sources avoid file listing together. That's great. It scales even better than v2. And this is amazing. We don't need to have Kafka or Kinesis in the middle anymore. These event-based file sources would give us all this new data. We don't need to centralize anymore. We could just read all this data immediately without having to do any listing. So we just simplified our pipeline by a huge margin. Just deleted hundreds of lines of code. And it became easy to replicate across clouds and regions because these event-based file sources, they provided the exact same semantics on Azure and AWS. So the business logic was the exact same. The source configurations is the only thing we had to change when we were replicating. Then structured streaming, we added this run once trigger. And this is pretty cool because the run once trigger says you don't have to run a streaming job 24/7. The run once trigger says I'm just going to figure out whatever is new, and I'm going to write it out as a batch job, and I'm just going to stop my stream. So you can schedule your structured streaming jobs with the run once trigger as batch jobs. And it's totally up to you how long, how often that you want to schedule these. And it just like cuts out the whole bookkeeping mess out of the problem. And Delta made GDPR easy. So those were all good, but what did we have to pay for it? The latency went from like 15 seconds to 5 minutes for the general case, because like files were uploaded to the blob storage systems every 5 minutes. But we were fine with that. That wasn't a problem on our end. So other techniques that are available is there's this thing called S3 inventory. It gives you all your data, all your metadata of files that are in an S3 bucket. So what we did with one customer was that they had millions, hundreds of millions of JSON files. They could not even list the directory. It was like 8 folders deep. It was basically impossible. So what we did was we took the S3 inventory, we turned it into Delta's transaction log. We didn't need to file list anymore, and then we just processed all that data, years and years of data, and it created great value for them. Another connector that we have is the S3 select connector. And what S3 select does is that if you have like JSON files or CSV files, you push the filtering of your data to S3. So when you're reading less data off of S3, then you don't have the like lots of small files problem anymore. You've already reduced your data size when you're running your queries. And other advanced things, like we could now leverage continuous processing with structured streaming to process data from Kafka and write to Kafka at sub-millisecond latencies. So if you wanted alerts of machine in the loop alerts, you could leverage continuous processing to build such pipelines. So to summarize, going over the problems again, file listing and many small files hurt performance. Delta and event-based notification sources help us avoid listing, so solve these problems. And Delta's inbuilt compaction and indexing alleviates small file problem. The HiveMetaStore is generally a bottleneck for large tables. Delta uses Spark jobs to manage its metadata, so it can scale to billions of files. It auto updates, no need to run refresh table, MSCK repair table. Partial distributed failures can taint tables, while the ACID guarantees of Delta guard us against garbage data. And you always get a consistent, and even like possibly stale if you want to, view of your table with Delta. Schema management and data hygiene are hard problems. The inbuilt schema management support only allows for safe changes. Invariants in Delta, prevent unexpected data from polluting your tables. This is extremely important for like ML use cases, where you expect like certain categorical values, or you expect certain ordering of columns. Basically, this makes sure that whatever you run your ML pipelines on, you get safety. And the Delta architecture, the bronze, silver, gold table architecture, makes backfills and corrections easier. And the rollback support that's going to come in Q4 is going to make corrections effortless. And the update and delete features that are already inbuilt into Delta support, help make GDPR easy. And I would really, there was a talk, 2 talks before me, by Paytm. They had a very similar, list of problems and solutions. And what I observed from there, they built this like fascinating pipeline. But what, struck out was they had 4 engineers working 8 months to build all that stuff. But this already gives it to you out of the box. So hopefully it should make your life easier. So for further reading, I have a list of blogs on structured streaming and Delta, processing petabytes of data, fast DNA sequencing. You could all do all of this now with structured streaming and Delta. So thank you all, and if you have any questions for my prepared answers, I'd be happy to take them.